Before we try to understand laws of motion, we go to Galileo's experiment. By observing the motion of objects on an inclined plane, Galileo concluded that objects move at a constant speed when no force acts on them. Here are some examples. Let us have two frictionless smooth inclined planes at the same inclination, as shown here. Let us allow a smooth frictionless ball go down. Its speed increases. Is maximum here at the bottom. Now ride up and tend to reach the same height. Now, if we let the angle of inclination of this inclined plane 0, then the ball will tend to go to achieve the same length equal to this height, and then stop. Galileo thought it is because of some kind of unbalanced force. Question is, where does this unbalanced force come from? Galileo's answer was, it comes in the form of a frictional force play against the smooth moving ball. And ball stops. Here is this man driving a car. The man tend to remain at rest with respect to the seat. All of a sudden he applies brake. The car slows down. But body is tending to remain in the same state of forward motion. Could have collided, but being tied with the belt is saved. So Galileo explored this property of inability to change its position of rest or motion is named inertia. Then came Newton, studies Galileo's phenomenon and gave 3 laws of motion that govern the motion of objects. These 3 laws are known as Newton's laws of motion. The first law of motion is same as Galileo's law of inertia. That states, if a body is moving, will move. And if at rest, will be at rest, unless or until we apply some force to stop it or to move it. This is Galileo's law of inertia or Newton's first law. We put a card over a glass. And a coin is placed over it. When the card is flicked with the finger, the coin placed over it falls in the tumbler. Reason: coin at rest, like to be at rest. That is inability to change its position of rest. This is inertia of rest. When a fast-moving carom striker hits coin pillar, only the carom coin at the bottom of a pile is removed. Reason is coin pillar is at rest, like to be at rest. Only the coin hit is removed. This is another example of inertia of rest. We are now interested to know whether all bodies have same inertia. What relation is between mass or inertia? Let us take some examples. As we know that it is easier to push an empty box than a solid box. Similarly, suppose we have a football and same size of a stone. Kicking a football will fly away. But kicking a stone with equal force will hardly move. In fact, get his foot injured. Clearly, heavier the body, larger is inertia, or lighter is the body, smaller is inertia. That means inertia is the measurement of its mass. So we can say inertia is the tendency to resist any change in its state of rest or motion. When we apply an unbalanced force onto a body, change in velocity with time takes place. Means acceleration is produced. Larger the force, larger the acceleration. When a body hits an object, impact depends upon mass and velocity. Newton called it as momentum. Written as P.So momentum can be defined as amount of motion produced. That is, mathematically P equals mv. SI unit of P equals kilogram m upon s. Let a body of mass m is applied with a force F at a. The body moves with a velocity u, reaches b with velocity v if time taken as t, and acceleration produced as a. Then, change in momentum equals final momentum P2 minus initial momentum P1 equals mv minus mu. Now by Newton's second law of motion, rate of change in momentum equals F. Therefore, F equals m, v minus u, upon t. F implies that F is equal to m into v minus u whole upon t. But v minus u whole upon t is equal to acceleration a. Hence F is equal to m into a. From equation 1. Cross multiplying we get, Ft is equal to mv minus mu. That is, force applied for a very small interval t changes the momentum of the body. Ft equals impulse, mv minus mu equals impact. So the Newton's second law of motion states, rate of change in motion of a body is directly proportional to the force applied. One of the practical example of Newton's second law is, while catching a ball, fielder draws his hand back. Why? Answer is simple. While catching the ball, impact of the ball on hand is maximum. In order to avoid any injury, the fielder draws his hand back. As a result, reduce impact to zero. Another example is, hitting a football means applying a force that give rise to change in rate of momentum, means produces acceleration. Now we shall try to do some MCQs. Question number 1, I read as, which of the following statement is not correct for an object moving along a straight path in an accelerated motion? Options are A. Its speed keeps changing. B. Its velocity always changes. C. It always goes away from the earth. D. A force is always acting on it. When a body is moving along a straight path in an accelerated motion, there will be changing in speed. Velocity will change. A force is always acting. But to escape out of earth, the object needs gravity more than that of earth. Hence, C is wrong. A goalkeeper in a game of football pulls his hands backwards after holding the ball short at the goal. This enables the goalkeeper to A. Exert larger force on the ball. B. Reduce the force exerted by the ball on hands. C. Increase the rate of change of momentum. D. Decrease the rate of change of momentum. Answer is B, because, as goalkeeper hold the ball, swing hand back. This reduces momentum. As a result, reduces force of the ball exerted on keeper's hand. Newton's third law states, to every action, there is an equal and opposite reaction, acting on some body. For example, let a book on the table. There are two forces acting. One is book exert this force acting vertically downwards. And this force is the reaction, acting vertically, equally upward, exerted by table onto the book. So action or reaction are not acting on same surface, but acting on two surfaces. We take some visual examples. Let us have two springs tied together with the wall is shown in the diagram. When we apply a force as shown, first spring reads action and other reads reaction. Both are reading same. Means action and reaction are equal and opposite. Both acting on two different surfaces.